today with us because she's really an outstanding scientist. And she's from Italy, Salernitana. So she studied at Salerno University, and then she got a PhD degree at the University of Rome, La Sapienza, already working in gamma reverse associated with supernova 1BC and the theoretical interpretation within the fireball model. Advisor was Professor Remo Ruffini, whom I know quite well, so a wonderful person and scientist as well. And then she got a IRAP PhD cycle to obtain the doctorate, as I said before. And then she also was in collaboration with ETH Zurich and Freie Universität Berlin, Observatory de la Côte d'Azur, Université Denis Sofia Antipolis, and University de Savoia, and the University of Ferrara. Right now, she's assistant professor at the National Astronomical Observatory of Japan, also assistant professor at Sokendai, as well in Japan, and is affiliated senior scientist at the Space Science Institute in Colorado, USA, and visiting assistant professor at University of Nevada, Las Vegas, also in the United States. Her research expertise is quite ample, I would say. I mean, she mainly focuses, but not only, in high-energy astrophysics, mainly gamma reversed quasars, and also she's working in selection bias and statistical methods for astronomical data, also in active galactic nuclei, and also developing machine learning techniques which she applied to gamma reverse and to active galactic nuclei. And she's world famous in our field, I would say, because she discovered a relation in the gamma reverse afterglows between the luminosity and the end of the plateau phase we see a few hours after, or even a few days, and the rest frame duration. And also in the luminosity and the peak luminosity of the prime emission. So the first relation, which is the one which you have the name on it, is called the Dainotti relation. So she's well known for this. And this other second relation is also very important for us to study gamma reverse. The application of these relations in combination with supernova type 1a and cosmic microwave background radiation led her to obtain compatible results with those previous probes, showing the validity of this relation as cosmological tools. So Giovanna is also expert in cosmology and also in the application of these relations to cosmology, as you will see. So recently, I think it's worth to mention that additional studies by her and collaborators show the reliability of quasars as standard candles, as well as the statistical assumptions commonly used for supernova 1a, quasars, and baryon acoustic oscillations, which are really challenging. So the use of more accurate statistical assumptions have reduced the uncertainties of cosmological parameters to 43%, and I think she will tell us about this in this talk that we are all looking forward to hear. So I will not tell you anything else. She has a lot of publications and a lot of recognition, but I think it's time for you to tell us. We're looking forward to it. Thank you so much again, Maria Giovanna, for coming here.
Thank you so much, Alberto, for inviting me. It is a pleasure to be here. It is the first time for me in Granada, so it is the first time in the institute. So today I will tell you about. You want to get the microphone? Yes. So can you hear me well? Yes. So today I will tell you about how to reduce up to 35 and even 40% on uncertainty on the cosmological parameters on several probes. So first of all, what can we investigate with all these probes with gamma ray bursts, Supernovae 1a, quasars, and baryoacoustic oscillation? Of course, we would like to cast light on the content on the dark matter, which is currently 26.8% of dark energy, and we know that the atoms are only almost 5%. And the interesting point is that I started this analysis with supernova 1a because actually I wanted to combine supernovae and gamma reverse. And then a new window of avenue of research opened up to our eyes. And this paper that we started to investigate in 2021 were actually highly cited. We are now in the top 1% cited paper in the Web of Science. So what did we discover back in 2021? First of all, we wanted to investigate this, how these different probes show us that there is a discrepancy between the late universe and the early universe. So basically, you could see that the data from Planck, they have a discrepancy that goes between 3 to 5 sigma compared to the Hubble constant obtained with supernova 1A. So here you have the Hubble law and this tension that it is possible due to evolution or the evolution of the parameters, and there are several papers in which we explain what could be also the theoretical interpretation out of those. And here we define the H0 as the ratio between the scale factor and its derivative. But nowadays, and this is a paper we recently published in Journal of High-Energy Astrophysics, what it is the current situation? Because 100 of years ago, okay, what was the Hubble constant? Maybe 50, maybe 100. And there was a fight about this. And then, suddenly we settled about 70, and we stayed on the value of 70 for many years, but suddenly, 10 years ago, again, there was an issue because of this discrepancy between the data of the Planck and the supernova 1A, and what it is the situation now. I would say we are almost back to square one, in the sense that if you consider not only the supernova and the data of Planck, but you also consider other probes, and of course, I would like to mention also the gravitational waves. You see that, of course, we have only one measurement, so the error bars are very large. But basically, if you see the error bars, you go from 55 up to basically 95. So the error is large, and we need to wait for more years to come and more observations to reduce this uncertainty. But also here in this analysis, we also considered the gamma ray burst, and I will tell you about this later. But anyway, depending on the sample size, depending on the probe that you are considering, you really go with the discrepancy that it is beyond 3 sigma, in some cases up to even 6 sigma. And so what people have done and what we have done also in this field is to consider the calculation of the observed distance moduli from a set of given parameters of the supernova. So here we have the peak magnitude in the big B band, then the absolute magnitude. This is a linear combination of quantities, and this is a 3-parameter correlation, which is called the Philip relation. It started from the famous 2-parameter Philip relation. And here we have the absolute magnitude, then we have the stretch parameter, the color, and the host galaxy mass correction and the bias correction. Probably you have seen this formulation in different ways. For example, sometimes the host galaxy mass correction and bias correction are gathered together. But this is the formulation that has been used with the Pantheon sample data. And here we have the references, the B band with the stretch is put as 0 and color 0. And one point is that the M is degenerate with the H0. So if you vary the absolute magnitude, then you automatically are varying also Hubble constant. And in this paper, basically, we let the Hubble constant vary. We do a tomography in redshift beams to understand if there is an evolving trend, either of the parameters or the Hubble constant. But now, if you consider the theory versus the data, basically you have this, you want to compute the chi-square and consider the residual between the observed magnitude and the theoretical one. And with the theoretical one, you can assume your own cosmological model And here you have these errors in which you consider the covariance matrix, which includes both statistical uncertainty, diagonal part, and the systematic contribution. These are the off-diagonal terms. And I would like to put up an important caveat here, because in many papers in the literature, the off-diagonal terms has been neglected, but in the paper that we are tackling, it is always included. And it is important because it may actually change, make variation in the results. So here we have the chi-square defined as in this way, with this covariance matrix C. When we consider the baryoacoustic oscillation contribution, then we have to sum up the contribution of the both chi-squares. And here, of course, instead of having the distance or luminosity, you have the comoving distance, which is defined in this way. And basically, it is the same structure as before. Instead, again, of the distance volume, you have the comoving distance volume, that it is defined in this way, where here we have the sound horizon as parameter. Now, which cosmological models we can adopt? In principle, you can adopt with this setup any cosmology, and the cosmology that we are considering in this analysis for the supernovae are the one for which the radiation is neglected and also the curvature is neglected. So this term is going to be zero. But in some of the papers with the GRBs, because there were some papers in the literature that were showing that there is some curvature that is non-negligible, we also introduced this non-zero curvature, and actually gamma reports even point to non-zero curvature, but of course it is yet compatible with lambda CDM because the error bars are pretty large. And here you have also the parametrization with as a function of redshift of the equation of state. And basically this h of z can be written in this way, where instead of having, here you have the contribution only of this term, but here to add to this term, if you have departure from lambda CDM, then you have also this contribution, which is non-negligible, in which W0 and WA are parameters that can be written in this way. This is the parametrization of Chevalier-Linder-Kolarski. And this is quite a famous one, and it is a phenomenological one. Now, in the tomography that I told you that we did, we practically divide the supernova sample in several bits, 3, 4, 20, and 40, and we wanted to check whether the Hubble constant stay constant, as we expect to be. But actually, this is not we found out. We didn't find out neither in lambda CDM nor in W0WA CDM model. So here, in fact, you can see that we have a decreasing trend. And here we consider again the systematic uncertainty and the statistical one. And the normalization is set so that the absolute magnitude corresponds to 73.5. We have to recalibrate the absolute magnitude because in this sample, the Pantheon, the calibration has been done at 70. But we wanted to show that basically our results does not depend on the initial normalization. And this is done similarly in the W0WA CDM model. And here we have with 4 bins. Now, very interestingly, and completely separately from our group, another group in Greece was doing similar analysis, but varying not the Hubble constant, but rather varying the absolute magnitude. Because the absolute magnitude and H0, as I mentioned, are degenerate, basically those results point out to the same outcome, that regardless of whether you change the Hubble constant on M parameter, then you have a variation that it is not actually expected. Now, of course, one can say, okay, but this variation is quite rather small because you have large error bars, as you can see. And yes, it is true, but regardless of this, if you have a variation in the parameter, you really have to pay attention because this can mismatch, finally, your cosmological parameters. And when we consider also the baryoacoustic oscillation, we consider the 3 bins, and here we have the parameter that identifies this decreasing trend. Here it is the ratio between this parameter and the uncertainty, so this is 2 and 1.2 sigma. So it means that you don't have this variation that is quite large, but this in this paper, differently from the previous one, we are also varying omega m. So we are varying omega m with the Gaussian prior, so that we can be sure that this is not dependent. This result on some contemporaneous variation of omega m together with H0. And of course, we didn't vary in a uniform prior because the number of data points is yet not enough. We don't have enough statistics to have this variation in uniform prior. But of course, in the future, once we have more data, and I will measure in a moment our collection of this data with Supernovae, which would allow to vary even at 5 sigma from the Gaussian prior. Now, what are these results telling us, basically? They're telling us that there are 2 different possibilities. Either we have a new exciting physics behind this, so we have maybe a modified theory of gravity, we have slow rolling, we have several scenarios that can be applied and can work, and we are actually investigating this. But the other possibility, it has been at the center of the attention that there are still astrophysical biases or selection effects that may play a role, and they have not been fully investigated yet. So we are open to investigate both these possibilities, and then we can then point out to this astrophysical possibility that was also shown in this paper, Nicholas Perlmutter et al., in which there is the asymmetric distribution of the stretch parameter. So if the stretch is evolving, this evolution of the stretch can also influence the evolution of H0. So the question is, are we seeing an intrinsic evolving running Hubble constant, or actually it is the effect of other parameters that are evolving, and this effect is actually reverting to H0. So this is still an open question, and this new data can confirm this trend. There is also this paper that points out to 2 populations regarding stretch, and a clear trend of the Hubble residual. It's increasing with the color parameter. So again, we should pay attention to the classes also of supernovae that we are considering. But now the next question is that can we also use gamma ray burst to tackle this issue? And I would like to briefly introduce gamma ray burst, but because the audience is very expert on this, I will quickly go through this. So mainly, as Alberto mentioned, I've been working on the plateau emission now for several years. The plateau emission is a flat part in the light curve that happens between 42 and 60% of the total cases, depending on the telescope instrument that we are using and the sample, and it is around 32% if we consider optical data. This figure is showing the X-ray data. So this is the afterglow, and this is the Swift telescope, and this function is the Willigel phenomenological function. Now, this picture is showing only X-ray, but of course in gamma ray burst we have the optical and radio observation that can happen after days or months, and it is distinct from the prompt emission. And I'm particularly interested in the high-redshift gamma ray burst, because the high-redshift gamma ray burst actually can tell us more about the early evolution of the universe, and they can allow us to investigate population stars. Now, the point here is that you will see, maybe you have seen many papers in the literature that show correlations, but gather all the classes together. I think this is a bit dangerous because basically you are mixing up the different progenitors. And if you do that, when you apply the correlation for cosmological probes, then you can also have the problem of not properly using this tool. So, of course, we all knew about the short arc gamma reverse. These are coming from compact object merger, little sun, McCall, but there is now increasing evidence of the kilonovae that are observed with long gamma reverse. So this is even messing up more our effort to disentangle the progenitor according to the observation. And then we have the core collapse of massive stars for the long gamma reverse, but we have also observed recently supernova cases 1BC that are associated actually to short gamma reverse. So this is again a puzzling issue, and it seems that this classification is a messy business. So we also had in the past, in 2006, also the intermediate class of GRBs that are the short GRBs, but actually test like longer T90. T90 is the time between 5 and 95% of the total emission of the prompt, but with the properties that are harder as the spectrum as short gamma reverse. So the caveat here is that in the relationship that I used, we always have a look at the classes that we are gathering for the application for cosmology. And I mentioned already that we like using gamma reverse for a series of reasons that we can go beyond the epoch of ionization. Of course, it is not set at a given redshift, but if we can assume that at the end of the epoch of ionization it's at redshift 6, then with the gamma reverse in principle up to now we have gamma reverse observed at redshift 9.4, but in principle we can extend at a much larger redshift. And the problem is that GRBs do not seem to be standard candle because their isotropic energies, both in the prompt and the afterglow, they really span over several order of magnitudes. And of course, if you look at the prompt emission properties, the business is even more messy because there's a common motto in the GRB community that if you have seen one gamma reverse, actually you have seen only one. And this confounds our 20 years effort to gather common properties in gamma reverse. So this is a timeline of the effort of actually showing a correlation in the afterglow. Here, the luminosity time relation, it's an anti-correlation, and then you can combine with luminosity at the end of the plateau emission also with the peak prompt luminosity. So those together, if they are corrective for selection bias, they can lead to a three-dimensional relation that I will show you in a moment. Then we, in these years, when I moved to after I moved to NAOJ, then I started to investigate more the optical emission, also with the inclusion of the data from Subaru, and also with Alberto, we embarked in very challenging avenue to build the largest optical catalog, and I will mention in a few moments now. So we could use the optical data and the radio data to build this relation. So basically, we have now this luminosity time relation and this 3D relation that it is built in all wavelengths, starting from high energy, and I will show you in a moment, until the radio. And in radio, also other colleagues from China applied this as a cosmological tool. So here it is the 3D relation, as I mentioned, this is the peak prompt luminosity. So you see that these are the several classes. The short are the red cuboid, and the X-ray flashes as the sphere. And this cone are the GRB associated with supernova. So what we did here is that we segregated these classes. So also the gray color, it's for the GRBs below the plane, and the brighter color is above the plane. So what it is happening here is that you can see that the several classes are sticking out from the plane. So we should, again, if we would like to have shorter smaller intrinsic scatter, we should try to disentangle these classes. And what we found out is that the long gamma ray burst, not associated with the supernovae, and if we segregate also the X-ray flashes and of course the short gamma ray burst, they have the smallest intrinsic scatter, so the smallest distance from the plane. Now, of course, there are two competing factors for cosmology. One is that you have to have the largest possible number of sources, but also the smallest intrinsic scatter. And what it matters the most actually is the smallest intrinsic scatter. The second factor is the number of sources. So we are working on both directions here. But now, if we consider, I was mentioning about the fact that we have also cases in high energy. So here you can see that there are three cases of gamma ray burst observed by Fermi-Lat, that they have an indication of the plateau emission. And what happens to the relationship here? So basically those three GRBs, they lie at larger value of the luminosity at the end of plateau emission, but a smaller time. So this high energy gamma ray bursts, basically, they have shorter duration in the afterglow and more prominent luminosity. If we consider this is not a one-to-one comparison because we didn't have the observation in the XRT for these three GRBs, but I mean, only for like later time. But so if you have the LAT and the swift gamma ray bursts, you can see that the distribution of the duration is much smaller. So as I mentioned, we have also this in optical. And what we did here is the following. Basically, we computed the distance of the data point to the gold sample. So the gold sample is a sample of GRBs for which you have almost relatively flat plateau. And then we could upgrade this category as a platinum sample. So the platinum sample has no flares, no gaps inside the plateaus. And also we have a precise measurement for the uncertainty on the parameters in the definition of the plateau itself that it is given by the Willinger function. Now, if we consider the selection biases, we have to correct for this. And here on the right-hand side, we have a correction for evolution. So all the variables of luminosity and time, they evolve. So basically, when you consider a high redshift, you will have to correct by this evolution. And usually the correction for the prompt luminosity is around 2. So it mimics the evolution of function as 1 plus z to a given power. I can tell you, if someone is interested, I can tell you later about this. So I will not delve too much into the details of this correction for selection biases. We worked on this with colleagues from Stanford University when I was Fulbright and Marie Curie there. So if you correct for this biases, basically you will see that the luminosity is smaller, but it does not change actually in optical this mixture with the classes. However, in X-ray, you can see that the distances between each given GRB and the golden sample shows you that the short and long gamma ray bursts are different. So the fundamental plane can be also discriminant among classes. Does not work very well for optical, but if we use the X-ray fundamental plane, this is something that we can actually work out. Now, going back to cosmology, because this is sort of an overview to say which classes of gamma ray bursts we should use for cosmology. So there are actually two main methods to use gamma ray bursts as cosmology, but generally also other probes. You can do a simultaneous fit. So you fit the correlation parameters and the parameter of cosmology together in the same time. Or you can calibrate with low redshift probes, for example, with cosmic chronometer. And so given that objects have the same redshift, they have also the same luminosity distance regardless of the underlying cosmology. If you make this assumption, then you can use other probes. And why cosmic chronometer? Because at the center of the debate, there is the supernova 1A. So if we use the supernova 1A, somehow we are circular in the sense that then we cannot answer the question about the Hubble constant. So now, if we consider the solution about fitting parameters simultaneously, here we have that these are omega m and h0, so we see that the value are smaller than 70. But this analysis has been done with the supernova or the Pantheon sample, for which the h0 has been calibrated to 70. So we expect to have a shift towards 70. But so we can say that this result is mainly driven by the supernova, for what I told you before about the number of sources that matters, and also the scatter. But what happens if we consider only gamma ray burst and you do the realization of the MCMC multiple times, for example, 100 times? So, and you consider all wide parameters, so you can see that H0 actually is peaking towards 75. And this is, if you don't consider, for example, the evolution, or if you vary only H0, only the Hubble constant without the evolution of W. And W is peaking around -1. Now, the same situation applies if you fix also the evolution. And there is another paper of a student of mine, Leonard, in which we use quasars, but we built a setup for which basically we also change the omega m as a function of this evolving parameter. So this is the most, how to say, complete setup. Of course, the error bars are larger, but this is more realistic because we are including all selection biases that you can imagine at this stage. Now, of course, with these such error bars, one could be scared to even think about using gamma ray burst, because here you have basically 20% of uncertainty. But this is again uniform prior. If you use instead Gaussian prior, so if you already assume what are the values, for example, you're interested in one parameter and you are assuming Gaussian prior on the other, then basically you can get a percentage of uncertainty about 5%. So then gamma ray bursts become pretty compelling in terms of even precision. And what happens if we consider instead the method number 2? So if you use the cosmic chronometer as calibrator on the fundamental plane, here you can see that basically the parameters becomes very tight, because this is the 2D. So you see that the contour becomes to be much tighter, especially for the C0. And interestingly, when we consider evolutionary effects, it seems that the 3D relation works less well than the 2D. So it means that probably when we consider other calibrators, we can go back to the 2D relation rather than the 3D relation, because the B parameter that entails luminosity goes towards 0. So it is not as important as the luminosity time correlation that peaks around -1. In fact, if we consider the magnetar as the main factor driving the plateau, then it is perfectly compatible with the luminosity times exactly -1. And interestingly, this is compatible, this is sigma scatter, with the fundamental plane relation that we obtained in 2020. So with this analysis, we have consistently always smallest scatter in the literature for this relation. And actually, if we compare this relation with other relation in the literature, we also know that, for example, the peak-ISO relation depends on the sample size and also reach higher value, like 0.55, according to this paper in the literature. So this means that for the afterglow emission, this is the tightest so far relation in the literature, and it is also as tight as the prompt emission relation. And of course, this result came out after many years of work in terms of the selection biases, but also in terms of discerning among the different classes of gamma ray bursts. Now, I promised that I would tell you how we could reduce this 35%, 40% of uncertainty, and now we are here at this point. I was working with a colleague from statistics department, and she told me, okay, why don't we start from the scratch? I said, okay, let's start from the scratch. What does it mean starting from the scratch? So the question was, we use the statistical assumption that everybody use about the likelihood. So we are using the Gaussian likelihood. So it means that the residual between distance moduli observed and theoretical, we assume to be Gaussian. Then we use this Gaussian likelihood for all the analysis. But the question is, are Gaussian likelihood of the supernovae, BO, quasars and GRBs valid? No. The answer is they are only valid for GRBs, and we don't know whether it is true because GRB sample is small. So in the future, maybe we have to apply other statistics. Now, interestingly, if you consider the supernova 1A, then with the Pantheon sample, the logistic distribution fits better rather than the normal. For the Pantheon Plus, which is a collection of 1701 supernovae, the t-student works best, and this is the difference between Pantheon and Pantheon Plus sample. So these are heavily tailed distribution, and of course, if you use more data, it is expected that you will not find the perfect Gaussian. And the problem is that indeed, this analysis will lead you to have a different uncertainty cosmological parameter. I mentioned before that we have different contribution, right? So you have that the scatter matters, but also that this is the sum of the number of sources also matters. And now these are the probability distribution function for the t-student and the logistic distribution. So you will need to leave the parameters free to vary in the cosmological setting. Now, here finally we can see that if we use the logistic, you have a reduction by 43% and 41% for omega m and H0 respectively, and the t-student from 42 to 33% for omega m and H0 respectively. You can actually see visually this reduction of the scatter for the Gaussian and the logistic. And here, if we consider by acoustic oscillation of quasar and GRB, you see that for GRB, the Gaussian is okay, but not for the quasars, for which the logistic is better and the t-student is better for the BO. Now, we have not updated yet for the new data release for the BO, but this is something that we are planning to do in the near future. And if you consider this new statistics, what we did is to repeat all the analysis that we had in the past with this new likelihood, and we consider both flat lambda CDM and non-flat lambda CDM, and also the flat W CDM model. And we were using three different configurations, so no evolution, fixed evolution, and varying evolution, as I told you, that these are the three main analysis, but usually in the literature you will see only the no evolving case, so there is no correction for the parameters that they evolve. Here we use this for both quasars and the GRBs. And then in this table, this percentage is the percentage decrease between the assumption of Gaussian and the non-Gaussian assumption. So you will see that there is always minus, because we are always gaining a reduction of the scatter with this analysis. So it really goes from 20–35%, what I mentioned before. The only case in which there is no difference is the flat WCDM, in which there is no evolution. But for the rest, you have always a reduction in the scatter. So it really matters the statistical assumption that you make for the application for cosmology. And now, if you have all configuration, the Hubble constant is higher, as I mentioned for GRB, so basically you have higher values, so these are closer to the pattern sample results. What do we need to do for gamma ray bursts? Because, as I mentioned, we need many more. And if we consider the optical sample, we would need around 2000 GRBs to reach a good precision. This is the uncertainty on omega n. But if you consider that in gamma ray burst, you can have also some measurement for which the error is divided by 2, then you practically need to have much less GRB, around half of it. So what is the situation? The question is, how many GRBs do we need? How many high redshift gamma ray bursts do we need to have? How many more redshift do we need to have? How much more precise the measurement of the plateau needs to be, and so forth. So we started to ask these questions already 3 years ago in this paper. And good news is that if you would like to be comparable to the supernova a decade ago, a bit more, then this was reached already 3 years ago. But you need to use machine learning, and this is an effort that I've been doing in the past few years. So you need to increase the number of GRBs with redshift with this machine learning analysis, and also reconstruct the light so that there will be no gaps in the light, and then the plateau emission can be determined much well, so with the smaller uncertainty. And of course, we need to have many more GRBs, so the catalog work is really essential. And if we do this, we can consider that we need, for example, 390 gamma ray bursts with very well-defined plateau emission in this platinum sample, and this is reachable in 17 or 18 years from now. Should not worry about this statement now, because we have to add in this calculation, SVOM was not added, and also Einstein probe was not added, and also all the catalog information has not been yet added. So we have currently 535 sources with redshift that can be reanalyzed to check whether or not with this new data we will have more plateaus. And so this can be updated. So again, we need to increase the sample size to have a cosmology independent approach, and also to connect the theory with the quest for the standard set. So of course, we can ask help to the standard fireball model whether there is a subset of gamma ray bursts for which, sorry, for which maybe the standard fireball model could work well in some of the settings. We did a series of papers here, and the result was that currently, if we consider either constant medium or the fragmentation of the stellar medium, or medium equal to 2, we are not yet able to obtain a scatter which is smaller than the scatter that we have obtained already, segregating the classes of gamma ray bursts. So we need to work more on that, and this is the catalog that really gathers 455 telescopes, 570 instruments, and this catalog is gathering all the data that also at private communication, Alberto very kindly allowed us to have the data from the boats, and many other people in this collaboration. So you can go and download the data, select the GRB, and also calculate your own spectral index and download all the data all together. So here are all some of the instruments that we use, and this is also the Japanese side of the instrument that we were using. Basically, we are also doing an effort with the QSO observatory. This is a 1.05 meter telescope, so this is something that we can discuss further how to jointly make effort for this observational campaign. And this is what we are looking forward in the future, to have the flux time space so that we can then update the correlations. Also, the importance of having more data, because, for example, here you have data from the Subaru telescope, and here even those two data from the Subaru are critical to define the plateau emission. So again, the importance of the catalog, and we can, fill in the gaps in the optical light curve, provide spectra, redshift information with Subaru, identify new plateau, and reduce the uncertainty in the error bar. But now I don't think I have a lot of time left for the talk, so I will just quickly skim to the importance of the catalog and how other people can be interested in building this effort for the future. So we are working on the catalog to refine emerging features, new plateau, maybe also kilonovae properties, because we can go through the catalog information, check whether there are kilonovae emission which has not been seen before because we didn't have enough data, for example. So maybe there could be other cases, and then we can also have more precise measurement of the machine learning. Here we have the data collection, the homogenization of the sample, color evolutionary scaling, and division in the three different groups. The important point of the catalog is that we also remove the duplicate information according to the numerous filter. So if you have this information before the rescaling and you have coincident filter, you can rescale those in this way. And then we have also, if we don't consider the same time, then you have this recipe to have this, for which the time final time minus the initial time divided by the final time should be less than 2.5%. And this is what we provide here, the information of the observatory, the filter, whether or not it has been corrected for galactic extinction or not, and whether there is a flag in the data. So we have three different kind of flags. For example, some problems in the observations, and you can look in the table that we published. So why we have this 5%? Because basically you're seeing that the peak is around 5% of the difference in magnitude. So we take half of it. But now, basically, we have some color evolution analysis that tell us that basically either you can have variable slope for this color evolution or a fixed one. The results are similar, and because I don't have enough time, I want just to point out to this web tool, and you can use in your own even app. So if you wish to provide Lighthouse, new idea or tool, please contact me and we can embark in this new joint adventure together. Thank you very much.
It's amazing the work you are doing with all these GRBs catalog and talking many of us combining the data and then just filtering and correcting and so on, and then to come up with the possible correlation, especially with the use for cosmology. Yeah, I think it's really amazing. I have any questions, but surely we will discuss on our lunch. One of the things you mentioned in this plateau, yeah, we assume that it's due to magnetar activity. The fact that in gamma rays in Fermilab is shorter is just probably because we have, just a question, is that photons are cooling down, so we have more in X-ray time. So you only have 3 Fermilab events.
So this is thank you for your question, because the analysis that we did in that paper that was published in 2021 stopped in May 2016. And so the plan is that we would like to add this almost 10 years of new measurement, but because the analysis was done, this is a category 2 paper, so it means that we did a different analysis from the catalog, so we were integrating a different time to find more photons. So It was done with the 3ML, that is more sophisticated tools, so it takes more time to do that. But the point is that even though we stopped at 2016, these are rare events because it's 3 out of 16, so it's very small number. Regarding the possibility of the plateau emission, not only the magnetar is one candidate. I mentioned this because it is probably one most accepted. But we also recently published a paper with a student of mine, Leonard, in which we show that black hole spin down is also a possibility. And the relationship basically it identifies which are the region of allowed spin period and also the mass accretion onto the black hole that are possible if you look at this relation. Of course, one of the next steps would be to try to understand if for a given GRB we can distinguish whether or not for sure it's a black hole spin down or, for example, magnetar. And because there is degeneracy with the parameters, we don't know at which level we will arrive to have maybe a subset of gamma reverse for which we can say that it is one or another. Yes.
Very interesting. Also, you mentioned about the stretch factor, which is varying with redshift. What's the explanation behind that? I mean,
so the point is that many variables vary with the redshift. So, for example, also in GRBs, you have the time at the end of the plateau emission that can vary with the redshift, so you can have a correction. So basically, and for the luminosity, you have that the brightest GRB actually they are dimmer because you have intrinsically dimmer because you have to correct for this function that's 1 plus e to a given power. So we will observe also due to the Malmquist bias, we will have more numerous bursts at high redshift that are brighter, but intrinsically these are fainter because you have this missing population.
Sure. I mean, this is some sort of rate we are all trying to catch the highest redshift.
Yes.
Because we know it's very important for relations to extend the relations to this value. But I will ask you one question later, last time, but I want just to give the chance to people in the audience or by Zoom who may have some questions. So, anyone here? In Zoom we have some. No.
No, I'm watching, but not yet.
So how's now? It's okay.
It's 1:30 on the dot, so we could end if you wanted to.
Okay, so we continue discussion afterward. So I asked a big applause to Maria Giovanna for her wonderful talk. Thank you.